electromagnetic energy into space. And another is the reception, collects electromagnetic energy from space. In two-way communication, the same antenna can be used for transmission and reception. So now here, this is a brief history of the antenna. Maxwell equations comes in 1864 because Maxwell has predicted there is electromagnetic wave is there. Because whatever communication we are looking nowadays, now all these are based on the electromagnetic. If there is no electromagnetic, it means there is no communication. So now later on, the Hertz in 1888 discovered the parabolic metal cylinder. Then in 1901, Marconi has proved the transmissions of the electromagnetic wave. In the World War II, there is a radiating aperture, reflectors, arrays, and all these was invented. In 1968, Harrington used the method of moments. And 1974 to 81, there is a uniform geometrical theory of diffraction. So now these are the basic analysis methods and the history of the antenna. So now here the basic definition of antenna is an antenna is a circuit element that provides a transition from a guided wave on a transmission line to a free space wave, and it provides for the collection of electromagnetic energy. Another definition is in transmit system, the RF signal is generated, amplified, modulated, and applied to the antenna. In the receive system, the antenna collects electromagnetic waves that are cutting through the antenna and induced alternating current that are used by the receiver. And this antenna has a property of the reciprocity. So an antenna ability to transfer energy from the atmosphere to its receiver with the same efficiency with which is transfer energy from the transmitter into the atmosphere. Antenna characteristics are essentially the same regardless of whether an antenna is sending or receiving electromagnetic energy. Another important property of the antenna is the polarization. Polarization is the direction of electric field and is the same as physical altitude of the antenna. A vertical antenna will transmit a vertical polarized wave. The receive and transmit antenna need to process the same polarization. If the antenna have a different polarization or there is a cross polarization, then we will not receive the signal. So now these are the certain properties of the antenna. So now here the basic antenna concept. So now here this is the generator, and now it is connected through a transmission line, that is the guided TM wave, one dimensional wave. And when we flare it, then there will be electromagnetic wave will be propagated in the space. So the antenna is a region of transition between a guided by transmission line and a free space wave. The transmission line conductor separation is a small fraction of wavelength, while the separation at the open end of the transition region or antenna may be many wavelength. Antenna radiate or receive energy, transmission line guide energy. Why does antenna radiate? If the charge is moving with uniform velocity, there is a radiation. If the wire is curved, bent, discontinued, terminated, or truncated. If the charge is oscillating in a time motion, it radiates even if the wire is straight. The types of the antenna. So now here various types of the antenna is there. So now there is an isotropic antenna, idealized, radiate power equally in the all direction. So that is called the isotropic antenna. Then initially the antenna was invented, that is the dipole antenna, that is the half wave dipole antenna or Hertz antenna. Then quarter wave vertical antenna or Marconi antennas. Then later on parabolic reflective antenna. So I think you people have seen in your roof, because now just we are using for the parabolic disc for the TVs. Schematic diagram of basic antenna parameters, because now for every applications now we have to design the antenna. So now antenna has so many parameters. So now these parameters is classified into the major category, that is the circuit quantities, where we have to measure the radiation resistance, input impedance, noise temperature. Another is the transition region, where we have to see the current distributions. Space quantities. In case of the space quantity, we have to see the radiation pattern, power density, high power beam width, directivity, gain, effective aperture, radiated power, polarizations. And finally, we have to calculate the bandwidth, efficiency, and complex equivalent length. So now these are the parameters. When we design the antenna, then we have to keep in the mind. So now these quantities we have to measure. Antenna with a communication system. So now here the very basic diagram is given. So now here this is the transmitter, this is the receiver. So now this transmitter is connected through a cable to the antenna. Then there is a free space in between. So now if the electromagnetic wave travel from this transmitter to receiver, now there is really certain losses is there. So now these losses is called the free space losses. And now the signal which reach to the receiving antenna, and again there is a cable and the receiver. So now just we will get the transmitted signal at the receiver side. Now next is the antenna applications. So antenna has a various applications because nowadays we people are using the wireless system. Earlier we have a wire system, and the whole wire system is almost 90% is replaced by a wireless system. So now here the ground-based telecommunication system, direct broadcasting, radio links, mobile phone you already have in your pocket, and base stations. So one of the best example of the wireless is your mobile. So traffic toll, navigation, satellite communication system, linking ground-based station at long distance, satellite TV, mobile earth terminal, mobile phones, civilian and military radar, weather radar, air traffic radar, military search and scouting radar, synthesis aperture surveillance radar, pollution, traffic, fishing, borders, and all these. So now everything can be measured with the help of this antennas. Ionosphere and planetary research, radiometry, military early warning system, radio astronomy, meteorology, and land resources surveillance. And another is the antenna types. So antenna is classified in so many ways. There is a number one is the electrical small antenna. Their size is very small. Resonant antenna. Resonant antenna means now this will work as like a resonant structure, and now it work on a single frequency. Or it means we can say now there is a fractional bandwidth will be very small. Broadband antenna, aperture antenna, then array antenna, because now single antenna is not sufficient to transmit the signal. So now we people are using the array of the antenna. So now that is called the array antennas. And these are the name of the different antennas. So now there is a dipole antenna, Holdell dipole, monopole, loop antenna, helical antenna, transitile, dish antenna we are using in the rooftop. Earlier we have a Yagi-Uda antenna for the TV reception, page array antenna, microstrip patch, RFID tag antennas, UWB antennas, variable antennas. Because now here we will discuss the variable antenna. Variable antenna means now we can wear this antenna. So now that will be used as a flexible antennas and all these. So now next is the smart antennas. So now here this is the basic horn antennas, E-plane sectoral horn. So this is the H-plane sectoral horn. This is the pyramidal horn. So now here the extension is TE10 mode. That is a transverse electromagnetic. So now here the impedance matching through a floor. If now this impedance will not match to the antenna, then signal will not transmit. So now there is a gradual transmission with minimized reflections. Another is the slot on waveguide walls. So now here this is the waveguide structure. So now just we put a slot. So now the radiation is maximum at maximal interrupted current. So another is the patch structure. So this is the microstrip antenna. So now we will discuss in detail later on. So now here we have this is the substrate. Then above this is the metallic patch, and now this is the feed, and these are the electric and magnetic field lines. So now here come to our topic, because now here just I have given the very brief idea about the antennas, or just we have to review the basic quantities and all these. And now come to the biomedical applications, because here today I will discuss the biomedical application of the antenna. The antenna design are mainly for microwave, medical diagnosis, and data telemetry system. Two types of the antenna were designed: on-body match antennas for microwave medical diagnosis, and implantable antennas for data telemetry. So now the one is the on-body match antenna, another is the implantable antennas. These antenna is implanted inside the body. So now here The implantable antennas are used for the data transmission between implanted medical devices and external devices. Now there is just we have put the one device inside the body, and now it will be connected to the external devices. The on-body matched antennas are used in diagnosis applications such as cancer, brain disease, etc. So now just we will put the antenna on side of the body. So now for wireless data transmission of IMD, IMD means implanted medical devices with external devices, the implantable antennas are located together with IMDs in the human body and surrounded by different human tissues depending on the applications. That is referred to the skin, fat, muscles, etc. These antennas are designed to be matched to the human body to strongly reduce the reflection at the boundary of the air and the skin. Because now here this skins and the air will create the problem when we design the antenna, because now we have to put the antenna on the surface of the body. So now hence the dielectric property of the different human tissues and complex multiple layer human body must be taken into the account, because now their tissue densities and their dielectric properties and other are different from person to person and depends and vary from the age to age also. So now here the challenges of the antenna design with regard to the efficient design process are miniaturization, application specific performance, characterization and verification of the antenna. So now there are so many challenges to design these antennas. So now here this is the one of the example of the telemedicine for a healthcare system. So now here you will see, now this is the a patient. Here we are using the implantable antenna is inside the body, and on body match antenna is also placed, and now just we are receiving the signal. So now here we have to, so this is the wireless connected. So now here we can easily monitor the patients. So now for this purpose, now there is a characterization of human tissues, then characterization of the body match antenna is required. Then we have to design of the implantable antenna. So now here we should know how we design this implantable antenna for the body. And now next is the on-body match antenna. So now here the design of the on-body match antennas, then micro imaging. So then with the help of the combined system, and nowadays now we are talking about the internet, IoTs and all these. So now this is the one of the best examples. So now here for this purpose, now we people have to design the antenna, whether we are using the antenna on the body or we are using the inside. And all these are connected wireless. So biomedical telemetry permits the measurement of physiological signal at a distance through either wire or wireless communication technology. So now this signal can be connected with a wire or wireless. So depends on the environment. So now physiological signal are obtained by means of appropriate transducer, post-processed, and eventually transmitted to exterior monitoring and control equipment. So one of the latest development of biomedical telemetry is in the field of implantable medical devices. Because sometimes the patient is far away from us and we have to monitor the patient. Because now in the COVID days, so now the doctor will not touch the patients. So now if we have a certain types of the technology, then we can put the implantable antenna and the old type of the sensor on the body, then we can easily measure the progress of the patient with the proper isolation, because there is no need to touch the patient and we can easily collect the data and we can easily, doctor can easily treat the patient. So now here this play a very important role nowadays. Everything should be a wireless, right? So now here the biomedical applications using electromagnetic waves require implantation of antenna inside the human body, because sometimes we have to measure the certain parameter inside from the body. Sometimes we have to measure from the outside. So now there the implanted devices inside the human body is aimed at collecting the patient information and to send it to the base station through wireless communications. So now once the signal is reached to the base station through a wireless communication, then we can send anywhere. So now if the doctor is sitting in the USA, and now the signals can be easily sent to the USA, and now he can monitor the patients and he can give the good advice to the patient. So now this is called that we can say now this is an online monitoring system, right? So now here the implantable antenna inside the human body have two types of biomedical applications. So they are biotelemetry and biomedical therapy. So biomedical biotelemetry can build a wireless communication link between human body and outside environment. So now we have to put a certain sensors on the body, and the patient can be connected to the outside environment. Another is the biomedical therapy, and diagnosis include treatment of the disease, monitoring of various physiological parameters. So these applications reduce the healthcare cost by reducing hospitalization period of the patient. So now there is no need to come the patient to the hospital, because now in the COVID now there is a very big problem, because large number of patients and there is no space in the hospital. So now the person can be quarantined at his home, and now we can put the all devices on the body, and the doctor can easily monitor and he can advise the treatment easily. So wireless body area network is the healthcare monitoring system which uses implantable devices inside human body. This system provides home healthcare monitoring of the patient, because nowadays this home healthcare monitoring is very much needed because the person is quarantined at the home. So the model of the wireless body area network system is shown in this figure. So now here this is the we have put a implantable device here, and now it will transmit the signal, and now this signal is reached to the base station. So now here this is at the home, and when this signal will be transmitted and the data collecting system, and now it will reach to the doctor. So now this is the wireless body area network for home healthcare monitoring of the system. So now here there is a we require two types of the engineers. Now one is the now we have to design this wireless purpose for the wireless engineers, and other is the antennas. So now here this implantable antenna for biomedical applications. So now here this we can see here. Now this is the human body, and now here the base station. So now what we require actually. Now number one is the base station. In between there is a patients and this base station. Now there is a channel propagation is there. And now human body, now we have a insulations implantable antenna, because now this antenna will be inside the body. Inside the body means now we have a certain circuits. So then we again require electronic and power supply. So now this antenna will continuously transmit the signal. Another, we require the biosensors and the bioactuators. So various units in the wireless body area network in the system. So now these are the various units of the W-band system are base station, channel propagation, human body, insulation, implantable antenna, electronics and power supply, biosensors and bioactuator. So now with the help of all these, now we can easily monitor the patient progress. So now here just I will discuss what is the base station. So base station consists of several subsystems. So the subsystem include control module, receiving system and internet modem, because without internet we cannot transmit the signal. So control module store the information and it derive the entire system with the help of collected information. So receiver module receive the data using an antenna. So now here we require the antenna and send the data to the control module. So now we have to design such kind of the antenna. Now one antenna is required implantable, and another we have to transmit the signal to a far away. So now internet modem is helpful in interconnecting the modules using wireless data transfer. Another is the channel propagation. Propagation you already know, that is the propagation of EM waves, electromagnetic wave, between base station and implantable device need the analysis on scattering and multipath propagation, because we have to reduce this multipath propagation and scattering. Then we have to collect the proper signal from the body. So by reducing the above effect, the channel efficiency of propagation can be improved. Another is the human body. Human body is a hostile environment for implantable antennas, and it is highly dispersive, complex, and highly lossy in nature. So now these are the certain problems associated with the body. So while realizing the implantable antenna, the surrounding environment characteristics play an important role. So analysis, design, realization, and characterization are the different stages of the implantation. So now to design these antennas, now we have to include these properties. So now each stage must consider the human body as the surrounding environment. Another is the insulation, because now we have to insert the antenna capsule inside the body. So now there is a proper insulation around the implantable device, increase its efficiency and avoids any adverse reactions on the living tissues, because we have to insert. So now that should be compatible to the body also. So that's why the proper insulation increase the efficiency almost by 3 times the efficiency without insulation. Another is the implantable antenna. The implantable antenna is the key element in a W-band network, because now it will receive the signal and transmit the signal. So now the major objective to choose the radiator are compactness, cost and efficiency. So now it should be very small and there is a cost should be very low and their efficiency should be very high. The parameter for antenna design are radiation efficiency, bandwidth, coupling with the lossy biological tissues. So now these properties now we have to taken into the account when we design the implantable antennas. Now next is the electronics and power supply. The electronic component of an implantable devices allow functioning of the system, provide data communication and signal processing capabilities, and set the working power requirement. So the power supply having the largest volume occupation and set the lifetime of the apparatus. So now here we require such kind of the batteries. Now that should be very small and now it will give the power for the long time. So there is a several solutions such as energy harvesting, internal power supply or wireless power transfer are possible. So now here the energy harvesting, sometimes what happened, now there is a, we have put a one device inside the body and now with the help of the energy harvesting, now we can generate the energy, because sometimes the person is moving. Now suppose there is a one soldier is there and now he is wearing the so many equipments. So now just we can harvest the energy. So now here there are internal power supplies, wireless power transfers, there are so many ways. Now next is the biosensors and bioactuators. The biosensors and or bioactuators determine the application of an implantable device and its placement in the human body. Monitoring devices, for instance measuring temperature, pH, glucose, etc. or active system, that is the drug delivery apparatus, nowadays being investigated for implantable applications. Characterization and experiment. Each component constituting the healthcare monitoring system must be characterized to validate its proper functioning and the conformity with safety and regulatory requirement, because now we have to put the electromagnetic device inside the body and outside the body. Now then it should not be harmful for the patient. So now there is a proper regulation is there. There is how much power we can use. So now the all these restrictions we have to apply to design these systems. So now for this purpose, in virtue or in vivo or in animals, experiment are necessary steps before the application in humans. So now whatever we design, now suppose we design implantable antenna. So now first we have to do the experiment with the animals. Then then if the experiment is successful, then we have to go for the human beings, right? So now nowadays now there is a COVID vaccine is trial phase, na? So that's the same procedure. So now the wearable antenna for biomedical applications. So the fast development of wearable low power devices increased the requirement of solution for W-band implementation. The human beings are likely to carry a range of devices and sensors, including medical sensors, which constantly communicate with each other and the outside world, and these are very easy to carry. So the key technology to achieve this goal is a wearable electronics and antennas. So now here the microstrip patch is a well suited for any wearable application, because it can be made conformal for integration into clothing. So now you people have seen the microstrip antenna. The microstrip antenna is very light in weight actually, right? So now it can easily we work as a wearable antenna. So now here a wearable antenna is mainly used for biomedical applications. So body-centric communication system like paramedics, firefighters, military applications are utilized by different specialized occupation segments. So wearable antenna are mainly designed for the wireless body area network, that is for body parameter measurement. So now just we have to put the antennas and all sensor on side the body, and we have to take the body parameters. So the wearable antenna can be applied to all type of the aged peoples and for athlete for the purpose of monitoring heartbeat, blood pressure, fatigue measurement, and other parameters. So now just we put the sensors on the body and then we can directly measure the heartbeats, blood pressures, and all these. So wearable antenna is used for IoT applications by using them with combination of sensors. So now when we combine the all sensors with the internet and then we transmit the data, then it is the one of the best example of the IoT. So wearable antenna should be light in weight, very low cost, almost maintenance free, and with no installation. So now this is the prime requirement, because now the antenna should be very light, because now suppose now the this antenna we cannot wear on the body, right? So they should be comfortable and conformable to the body shape, but they should be highly reliable and efficient. So there are many problems with the application of wearable antenna. The major problem are they should be integrated onto a garments, increase the comfort of wearable. Antenna should be of minimum size. So now minimum size means now just we can use it as a buttons and all these. So now here the furthermore, it is difficult to keep the antenna flat and operating when people move. So the antenna under different bendings and crumbling conditions should include in design. So now suppose I want to wear an electronic device on my hand. So now here that should be bending. So now there is a bending type of the antennas we have to require. So now the body affects some of the major properties of the antenna, like the mismatch, which is caused by characteristics impedance of transmission line, electrical length changes, and continuously increasing losses, thus damaging its original operation. So now here our objective is to reduce the electrical lengths and all these. It means now the whatever we are placing on the body, so now that will be a complete transmitter we have to design on the body. So now it will transmit the signal, right? The interaction between the body and wearable antenna should include effects of the antenna on human body, effect of human body on wearable antenna, human body induced gain, human body arm efficiency, human body effect on impedance. So now here, this is the reconfigurable antenna for biomedical applications. So one of the example is given here, application diagram for body-centric wireless communication. So now here the body-centric wireless communication system. So now here this is the patient, and now here we have a implantable devices. Implantable device. Now suppose the one of the device, it will measure the some parameters from the patients. So then the signal will be transmitted. So now here this is inside the room. So now what happened? So now here there is a signal maybe from the floor. So now here there is an incident wave with random polarizations. So the signal will directly reach here and maybe a multipath wireless channel. So now antenna with polarization reconfigurability. So now this will not create a problem to the receiving antenna, and the original signal we have to receive. So now the different type of the analysis we will use for this purpose. Another is the biomedical application of the antenna. So one of the example is given. So now here the weight machine is given here, and another antenna is put on the body of the antenna. So now here the suppose I want to measure the weight. So now here there is just we put a transmitter here, then it transmits the signals and come to the network, and now this network will transmit the signal to a doctor as well as the dietitian. Now suppose this patient is losing the weight. So now the doctor is also know, and their dietitian is also know. So what type of the, now he can easily recommend the what type of diet you have to follow. So now here these all things are the wireless. So now a COVID days, now such type of things is required, because the doctor is far away from the patient as well as the dietitian is far away from the patient. So now we can easily monitor the patient. So now another is the one very widely spreading application in biomedical science is non-invasive method investigation for blood pressure measurement. So now here the old traditional way for checking blood pressure is called cuff method, and this is the new method is done with arterial tonometer, which is a biomedical application of the antenna. So now here we use the antenna, and now this antenna is used to measure the blood pressure. Another application is the bioelectrical properties of different tissues. So now here we have a tissues, one transmission antenna we have, and one is the receiving antenna. So now if the tissue will change the property, so definitely there is a receiving signal will change the property. So now here the penetration of the microwave property is used. The biological tissue absorb the microwave when an antenna transmit a quantity of a microwave to the tissues. The ability of a microwave absorption is different because the tissue with the high water content will absorb more than low water content. So now this you people have already experienced when you already we have a microwave on in our home. So now the some items is heat fast and some later on. So now here the rest of the microwave through the tissues will receive by another antenna and compare the quantity of the microwaves in receiver. The different tissue will be determined. So now here I have discussed so many applications of the antennas for biomedical applications. So now here first we have to design the antenna, and now the antenna should be very light in a weight and very small in size. So now that's why the microstrip antenna is the best suitable antenna for the biomedical applications. So now what is the microstrip antenna? So microstrip antenna is the microstrip plus antenna. So the microstrip, what is microstrip? The most popular type of planar transmission line used to efficiently carry energy between 2 points. So now here you people have seen the PCB. So now here this is the antenna can be designed on a PCB. So now here this is we have a ground plane, then there is a dielectric, and the top there is we have a copper. So now this is the microstrip. So with the help of this microstrip line, we have designed this antenna. That's why its name is microstrip antenna. So now here a microstrip patch antenna consists of a conducting patch of any planar or non-planar geometry on one of a dielectric substrate with a ground plane on the other side. The microstrip discontinuities can be used to advantage. So now here this is the structure. So now here the ground plane. Above the ground plane there is a substrate, and above there is a radiating patch, and now this patch is fed by a transmission line. So now this is called the feeding line. So now here the antenna made from patches of conducting material on dielectric substrate above ground plane. So now this is the actual fabricated antenna, right? The rectangular microstrip patch antenna fed by a microstrip line. So now here it has a certain advantage and a disadvantage. So now here the one of the beautiful advantage is a small size, low cost and weight. That's why it is the best suitable for the biomedical applications. Ease of the installation do not give rise to aerodynamic drag when used in aircraft, because here we are talking about the biomedical. So that's why the small size, low cost and weight, easy of installations. So that's why this antenna is used. So low profile antenna can be easily mounted to a metallic conductor or other surface. So this microstrip antenna can be easily put on the surface of the body. So no space for feed line is required. The feed line can be placed behind the ground plane, compatible with MMIC design. MMIC means now the monolithic micro integrated circuit. So whatever circuitry, suppose now just I design a transmitter. Transmitter means now there will be a diode, transistors, and all these are the components, and now one will be the antenna. So now if the whole circuit is fabricated in a single chip, so that is called the MMIC, and their size becomes very small in size. That comes in the millimeters and micrometers size. Only there is a big size will be only for the antenna only, and such kind of structures can be easily put on the body. They allow use of additional tuning elements like pin, varactor diode between the patch and the ground plane. And here it has a certain disadvantage: low efficiency, a small bandwidth, typically a few percentage bandwidth, low gain, low power handling capability. So now here the antenna has a different shapes. So you can design in any shape: square, circular, elliptical, rectangular, triangular, diamond, disc sector, circular ring. Whatever shape you like. Now suppose I want to design antenna And now this antenna should be placed in our belt. So now our belt buckle can be used as an antenna. Now suppose I want to design the antenna in the shape of my shirt button. So now the antenna should be in a button in shape. So now we can design in any shape. Now suppose I can put antenna in my specs also. So now suppose I want to wear the antenna, then I can put the antenna in the bracelet. So now you can design in any shape. So now the shape of the patch antenna is not a issue. We can design in any shape. So now here the construction and the geometry. Generally the microstrip antenna are thin metallic patches of various shapes etched on the dielectric substrate of the thickness h, which usually in the form from 0.003 lambda naught to 0.05 lambda naught. The substrate is usually grounded at opposite side. So now here this is the ground plane. This is the radiating slot because now it radiates from the two sides and other two sides will be there are in opposite. So that's why they will cancel to each other. So now there will be radiating slot, radiating edges is only two. So now here this is the microstrip antenna because it's a microstrip antenna and feed by the microstrip line. And now this is the probe feed antenna. There is a circular. So now here from the bottom side, now just we are connecting the connector, coaxial connector, then ground, and then dielectric substrate. So now the construction and the geometry. The dimension of the page are usually in the range from lambda naught 3y to lambda naught y2. The dielectric constant of substrate epsilon are usually in the range from 2.2 to 12. So now here we have to purchase a dielectric substrate because normal PCB cannot be used for the design of the antenna because their dielectric constant is not uniform. So the most common design use relatively thick substrate with lower epsilon r because they provide better efficiency and larger bandwidth. On the other hand, this implies larger dimension of the antenna. But in our biomedical application, we require a thin substrate. Then it can be easily wear on the body. That the choice of the substrate is very much limited by the microcircuit coupled to the antenna, which has to be built on the same board. The microcircuit together with the antenna is usually manufactured by photo etching technology. So now you people have already studied about the photolithography. So now with the help of the photolithography, we can easily manufacture the antennas. And nowadays there is a dry technique is there. So now there is a certain machines is there. Now just we put the geometry of the antenna and now it will print the antennas. So now here there is a single slot radiator. The feeding microstrip line dash line is beneath H on the other side of the substrate because this is the narrow slot. This is circular ring slot. This is the wide slot and this is the circular patch slot. So now here the patch on the different side and now there is a feeding line on the another side. So microstrip traveling wave antennas, because antenna can be designed in any shape, the open end of the long TM is terminated in a match resistive load. This is a comb shape of the antenna. So there is a comb microstrip traveling wave antenna. This is a meander line antenna. This is rectangular loop. This is a Frank line type of microstrip traveling wave antenna. So now we can design in any. So now here earlier we have discussed now the single antenna is not sufficient. So then we can design the microstrip antenna array. So now array, there are so many types of the array. So now one of the example or one of the photograph of the arrays is given here. So now here we have put so many arrays. Now come to the feeding method. Because antenna can be feed by the most popular method is the four methods. So now here the first method is microstrip feed, that is easy to fabricate, simple to match by controlling the inset position and relatively simple to model. So now here this is called the inset feed or microstrip feed. As the substrate thickness increases, surface wave and space feed radiation each increases. This is the coaxial probe feed. Easy to fabricate, low space radiation, difficult to model accurately, narrow bandwidth of impedance matching. But now for the biomedical application, we do not use coaxial probe feed, right? Because the antenna on the surface of the body. Aperture coupling. So now here this can be used. So there is no contact. So microstrip feed lines in the radiating patch are on the both side of the ground plane. The coupling aperture in the ground plane. low space radiations, easy to model, difficult to match, and narrow bandwidth. So now the different coupling has a different advantage and the disadvantage. So now according to our requirement, we have to choose it. So now this is the proximity coupled feed. So proximity coupling, there is no contact in between the patch and the feed line. So now microstrip line and the radiating patch are on the same side of the ground plane. So the largest bandwidth is up to 13%, relatively simple to model, has low spurious radiations. More example of microstrip and coaxial profits. So now here you can see center feed microstrip antenna. This is the off center. So now different shape. Now there is a rectangular, circular, triangulars, and ring. So now here there are various kinds of the feeding arrangement. So now center feed microstrip antenna. This is off center. These are the example for the profit antennas, and this is for the microstrip feed. Another is the criteria for substrate selection, because in the market now there are so many types of the substrate is available to design the micro components. But now according to our requirement, we have to select the substrate. Because now here suppose you want to design the antenna for the variable, and now suppose I want to put the antenna on my face or my hand. So now it should be easily bend. It means what type of the substrate I require? I require a flexible substrate. Now the substrate should not be hard, otherwise I cannot bend it. So now here there is according to the application we have to choose it. So now here there is a certain points is discussed. So possibility of surface wave excitation, effect of dispersion on dielectric constant, low tangent of the substrate, magnitude of copper loss and dielectric loss, anisotropic in the substrate, effect of temperature, humidity, and aging. Because nowadays, now there is a 365 days, now the temperature is vary. Sometimes we are in cold, sometimes in hot, and sometimes we have a humidity. So now it should not affect the operation of the antenna. Another requirement is mechanical requirement. There is a conformability, machinability, solderability, weight, elasticity, etc. And finally, the cost. Because now finally the cost of the antenna should be very small, low. Otherwise, there is no use if the antenna will be very costly. So now here another is the suspended patch antenna. So now here we are using the rectangular suspended microstrip patch antenna, because now here suspended means now here we have to introduce the air gap. So now when we introduce this air gap, then what happened? The dielectric constant will be reduced, effective dielectric constant. When this hello. So here this effective dielectric constant will be reduced. So now it will increase the radiation. So now it has a certain advantage of the suspended patch antenna. So very low conductor loss because of introduction of the air gap, provide flexibility to tune the resonant frequency of the antenna by varying the air gap, offers increased bandwidth as a result of increase in the height of dielectric region below the patch and lower effective permittivity. So now here it has a certain applications in airborne system such as aircraft, missile, rocket, satellite, in communication system for direct broadcast satellite reception and data transmission, as a radar altimeter antenna, for communication between satellite and mobile vehicle, and in satellite imaging system, in electronic warfare smart weapon system, modern GPS in biomedical instruments. So now here we will discuss the application of the antenna in a biomedical. So now this is the microstrip antenna is best suitable antenna for the biomedical purpose due to their low cost, small in size, and how we design. So now here all the design equations and steps is shown here. So now if you want to go in a detail, then you people have to refer the book of the C.A. Balanis of the antenna, or you may refer any microstrip antenna designing handbook. So now here the analysis is not I am not discussing here. So now here just I will show the certain design equations. If you want to go in the detail how we design this, the microstrip antenna related. So now just some of the YouTube lectures I have put in the RT website. So now you can download them and now you can listen, right? So now here just I will discuss in a brief. So now for the design of the antenna, first we require a specification. So now what type of the antenna we have to design? So now in the specifications, now there is a design frequency is given. So now suppose here for a ISM band we are using. So now first we have to know the operating frequency, then the substrate thickness, because we have to purchase the substrate from the market. Now suppose I am using a flexible substrate. So now what will be the thickness and all these? Then dielectric constant of the substrate and the size of the substrate. So now these are the input for the design of the antenna. So now here one of the example is given for this rectangular patch antenna. So now here this is your microstrip line feed. Their width is W1 and there is a Z0 is the characteristics impedance of the transmission line. Normally what is the value of Z0? Z0 normally value is 50 ohm. Why we take the 50 ohm? Because our measuring instruments port impedance are 50 ohm. So now here this Z0 and now this Z0 should be matched to the Z in of the antenna. So that's why in between we will use the quarter wave transformer. So now this is the lambda by 4 length. So that's why it is called the quarter wave transformer. So now their impedance will be somewhat in between the Z0 and Z-net. So now here to design this antenna, first we have to calculate the patch length and the width. So now here first we will calculate the width, that is 1 upon 2 pi. So this is the formula to calculate the width. Then with the help of this formula, then we will calculate the length. But now here in case of the length, now earlier I have shown you that from this side, this is the radiating edge. This side is also radiating edge. So now here what happened? So now here physical length is L, but now electrical length will be increased because now here certain electric field is from this side and from another side also. So now their electrical length is increased. So now here what happened? So now just I have to make a certain correction. If I will not make the correction, so then what happened? My antenna design, I will design the antenna on 10 gigahertz. Then this antenna will work on the different frequencies. So now here to calculate this delta L, to make a correction of this fringing field. So now just I will use this expression that the delta L upon H equal to 0.412 epsilon R effective plus 0.3 WIH plus 0.264 divided by epsilon R effective minus 2.58 WIH plus 0.8. And now here this what is epsilon R effective? Epsilon R effective is epsilon R plus 1/2 plus epsilon R minus 1/2 1 plus 12 H upon W power minus half. Why here we are considering the epsilon R effective? In case of the microstrip, now there is a certain electric field is passed through the air and some is passed through the dielectric. So now in homogeneous medium. So that's why here we will consider the epsilon R effective. Now suppose I design this strip line antenna, then we do not require this epsilon R effective. So now here, so now with the help of this formula, you can easily calculate the patch length and the width. Then I have to calculate the microstrip feed line dimensions because now this W1, but nowadays now you people have already a certain softwares that is HFSS, CSTs and all this. So now you can directly calculate it. But now earlier days, now we do not have such kind of the software. So now here with the help of this formula, because now this height of the substrate we know. So now with the help of this formula, we can easily calculate this W1. Similarly, lambda by 4 matching transformer. So now here this is lambda by 4 matching. This ZTR will be a square root of Z in into Z0. So now if the Z0 is 50, Z in is some 200. So now just you put here. Now this you will get the ZTR value. And with the help of this characteristics impedance of this quarter wave transformer, now just you put here, then you can easily calculate the width. So now here one of the example is given. So now here the design frequency is 10 gigahertz, substrate thickness is 0.762 mm, that is 30 mil. So dielectric constant of the substrate is given 3.2. So now here with the help of these are the specifications. So now with the help of these specifications, so now just we put in the earlier equations. So now here these are the formulas. So now just you put these values there. And then you will find out now the length will be 8.2 and the width will be this much, and W1 is the your width of the 50 ohm line, and this is the width of the quarter wave transmission. It means now I already know the all dimensions. So these are the theoretical calculations. So now with the help of this, now I will go for the CAD tools, right? So now here I will perform the CAD simulation. So now there are commercially available tool HFSS, high frequency simulation software, Momentum, Sonnet, CST, Microstripe, i3D, Ansoft, Empire. There are so many, large number of software nowadays we have in the market. And I think your college and I think almost in every college we have a softwares. So now with the help of this commercial available tools, now just we put the dimension in the software and then we perform the simulations. So now what are the steps for the simulations? So now here this is the simulation procedure. So define structure. Define structure means I already make a certain calculations. One of the example I have given for 10 gigahertz antenna. So now with that, now just I know the dimension, what is the length, width, and the all these. So now I have to define the structure. So now this structure will be defined in the simulation software. Then define the port. That is, we are using the waveguide ports and lump ports and whatever port we are using. Then define the material, because what type of the substrate material is there. Then define units and frequency bands, in which frequency band we are working. Then define boundary conditions, right? Whether it is a microstrip, strip line, so now depends, right? So now set the output parameters. Earlier I have shown so many parameters when I discussed the basics of the antenna. So now here you may set according to your requirement. So now far field, surface current, E field, H field, gain, directivity, whatever you needed. Then you can feed the output parameters. So when we run this simulation software, then it will give the output whatever you needed, right? So now here, this is the structure of the 3D EM simulator. Now just I have shown here, because now this quarter wave matching transformer we are using. Earlier calculation we have performed and we have calculated the W1, L, W, WTR. So now I know the all dimensions. So now with the help of this dimension, so now just I create a geometry here, because first I have to define the structures, then we have to define the all things, and then we have to run the simulation software. So now here output I have set, that is the S parameter. So now here this is the S parameter, return loss S11, and this is the S parameters phase in degrees. So and this is the radiation pattern in the 3 dimensions, and this is in the 2 dimensions. So now just I set these parameters. So when I run this software, then this will be a output for the simulation. If my simulation results are okay, then I can go for the fabrication. If not okay, then I have to optimize it. Now just making a certain small changes in the length and width and correction, small correction. That is the optimizations. So now here, this is the line impedance is 50 ohm. So another, this is the inside feed microstrip antenna. So now here, this is the simulation window is shown here. So now there are so many information you will get. What will be the wave impedance, line impedance, whatever, right? So now this is the inside feed microstrip antenna. So when we run it, now here this you people see that. Now I designed this antenna on 10 gigahertz, but now it's not working on 10 gigahertz. It is somewhat 9.8 or something else. So now what I have to do? I have to optimize this, because my requirement is now my antenna should be work on the 10 gigahertz. Similarly, the radiation pattern. So now this radiation pattern simulation radiation pattern will be shown like this. So now here this is the far field directivities and all these. So now here the main lobe magnitude will shown, directions, angular beam width, 3 dB beam width. So now here it will give directly side lobe also. So here this is the radiation pattern another. So now here this is the according to our requirement, that is we require E plane, S plane. So now just we choose the their degrees and all this, and we can easily draw it. So now this is another radiation pattern. So now if my simulation is okay, now my return loss, radiation pattern, whatever I needed, if everything is fine, then I have to go for fabrication. So now for fabrications, what I have to do? So now here for fabrication step, make the drawing in the AutoCAD or any other available software, make the mask using the available sources, because I have to follow the photolithography process. Then I have to prepare the mask, just like in your photolithography lab. I think most of the people have done in the first years. So now here the print the antenna using well-known photolithography technique. So now here just we take this substrate, then we clean the substrate, then we put the photoresist material, then we put the mask on this, and now the whole thing will go inside the ultraviolet sections, and then we remove the mask, and then we remove the unwanted photoresistors and all these. Then finally we will get the fabricated antenna like this. So now here the antenna is original antenna, fabricated is shown here. And finally I have to connect the connector, because without the connector I cannot test the antenna. So now here this is a gold plated connector, right? Sometimes the people purchase the local connector, but the local connector is not work for the high frequency, because now these are the lossy, right? So now here this when this my antenna is fabricated. So now here this is the inside feed microstrip antenna. This is the another actual fabricated antenna photograph is shown here, right? So now then next is, if I fabricated, then I have to characterize the antenna. Then I have to make a certain measurement. So now here for measurement purpose, now there is I have given only three quantities here: the return loss measurement, radiation pattern measurement, and the gain measurement. So now here this is the vector network analyzer. I think in your college, your Women Engineering College, Ajmer is also having this vector network analyzer. So now here this, with the help of this vector network analyzer, now you people can measure the return loss and all these. And this radiation pattern measurement purpose, now we require the NQX chamber. So now I have seen in your college, now you people have recently installed this or recently purchased the NQX chamber in your college. So now this is the all type of the experiment can be done in your college also. So right. So now with the help of this NQX chamber, so now just we put this antennas transmitting and receiving and all these, and we can measure the E-plane, H-plane radiation patterns, or in general we say now there is a radiation characteristics can be measured. So now here these are the measured return loss, and this is the radiation properties is shown here. So now here this is a parameter measurement. The magnitude of the reflection coefficient S11 is measured in automatic network analyzer for proper input matching. So now here this is the one of the snapshot is shown here. So here this is a radiation pattern. So now some people may not be know. So now the mathematical function of a graphical representation of radiation property of the antenna as a function of a space coordinate. So now here this is the radiation property of the antenna. So now here the antenna for antenna field region, because now here we have a reactive near field, then radiative near field, then radiative far field. So most of the time we measure the radiation pattern in the far field. And what is the condition for far field? Now this transmitting antenna and receiving antenna should have a minimum space in between 2d square by lambda. Then we will measure the far field. So most of the time, 99% we measure the far field radiation pattern. So now in the far field of an antenna, the radiating field can be treated as the local plane waves emerging from an imaginary phase centers. The advantage of the plane wave treatment, there exist only transversal field components. E and H are orthogonal to each other and in phase. And now this is a free space. E by H is equal to Z naught. So now here the mu naught upon epsilon naught square root. So 125, that is 377 ohm. So now this is the free space impedance. So now what are the radiation pattern? So radiation pattern is a graphical representation of radiation properties of an antenna depicted as a two-dimensional cross section, maybe a three-dimensional. And with the help of this, now we will measure the beam width. Beam width is what? Half power beam width, that is 3 dB in case of the dB. Measure of the directivity of the antenna, because now sometime we design the directional antenna based on this. So now just we have to measure the directivity. Reception pattern, receiving antenna equivalent to a radiation pattern. So now here this quantity we have to measure. So now here this is the radiation pattern. Mathematical expression is shown here. Now this expression is taken from the book of the C.A. Balanis, chapter number 14. So the far field for an undistributed patch antenna. So now here E phi theta, this is the expression. So now just we make a constant one item, phi, and then vary the theta. And when we constant the theta, then vary the phi. So where E and H refer to a elevation and horizontal planes for a linearly polarized patch antenna. Because in earlier, what happened? Earlier there is no simulation software when I complete my MTechs and all these. So on that time, now just in this expression we have to calculate it with the help of the calculator now just, and we have to make a calculations. So now the theoretical calculations of this radiation patterns was very time consuming, right? And then the MATLAB will come, the people have put the formula in the MATLAB and then we calculated it. But nowadays, now the life of the engineers is so fine nowadays. Now he can easily measure the radiation pattern with the help of the simulation softwares. So now here the radiation patterns. So now here the back lobe, back side, this is the front side, this is the main lobe, and the beam width can be calculated 3 dB down. So right. So now with the help of this is the horizontal pattern, this is the vertical. So now E and H plane can be calculated. Another important quantity is the antenna gain, because the gain is very important. So now what is the definition? So the power output in a particular direction compared to the produced in any direction by a perfect only directional antenna, that is your isotropic antenna. Effective areas related to a physical size and the shape of the antenna. Antenna type selection, because now this is the one of the important point, how we select the antenna. Because now here I am talking about the biomedical, so naturally now there's something different. Normal antenna cannot be used. So now here, what is the applications? Because in general, so easy of integration with the feed network, single resonance or multi-resonance, narrow or wideband, for example, UWB applications, so low frequency versus high frequency, available technology, integration level, cost, size, performance, power level, reconfigurable applications. So now here, these are the certain criteria to select the antennas. How we select the antenna? So now here I will discuss the few of them. They are used for the biomedical applications. So now here first I will discuss the design and development of configurable and reconfigurable UWB antenna for wearable applications. So now here we will design the antenna for the wearable application. So now here just first we have to introduce so miniaturization of communication devices leading to wear them. Body arm equipments are used for health monitoring also. Communication which involve body as a communication media is divided into three categories of body communications, on body communications, and in body communication. So performance of a body arm antennas with variations of a body proximity and orientation is required to be studied. Body centering ultra wideband communication is a promising area for research, because here just I have designed the ultra wideband. So now it demands for a high data rate. Why we require this ultra wideband? Because now due to the high data rate connectivity with minimum power consumptions, because because we have to store the power, and that is the data rate should be very high, then we can easily transmit the signal. Ultra wideband technology is a wireless transmission technique targeted particularly for a short range and low power radio communication systems, ideal for portable multimedia devices because of its inherent low power consumption and high bit rates. So now here this is the UWB spectrum. So now most of the people already know. So now here this is the range from 3.1 to 10.6 gigahertz. So this is called the UWB spectrum. So now here allows UWB technologies to coexist with existing radio services without causing interference. So now here this report and order, FCC report and order rules are designed to ensure that existing and planned radio services, particularly safety services, are protected. So now here FCC limit ensure UWB emission levels are exceedingly small. So now part 15 limits equals to minus 41.3 or 0.25 dBm per megahertz. So for comparison, PhD limits for 2.4 gigahertz, ISM, industrial, scientific and medical band. This is one of the important band because we have to design these devices inside this band. And 5 gigahertz bands are 40 dBs higher per megahertz. So now here certain UWB challenges is there. So now use large bandwidth should not cause interference to the other entities in the spectrum. Implies limit on transmit power to be legal. Receiver challenges. Receiver designed to acquire data and the noise. Wide RF bandwidth implementation. In-band interference. Global standardization. Broadband antennas. The UWB antenna with compact size. Wide impedance bandwidth, simple structure. Only directional radiation pattern. So now here, this is a summary of preliminary report and order. So now here for imaging, because we are using the for biomedical imaging sometime. So now here their frequency range is 3.1 to 10.6. It has a certain restrictions. So now here this through wall and surveillance and communication and vehicular. So now we will not discuss here. So now here, what are the requirement of UWB antenna design? Because here we have a certain requirement. Ultra wideband bandwidth where most of the energy of the source pulse is concentrated, steady with frequency directional or omnidirectional pattern. There should be a constant gain, constant group delay or linear phase. Why it required? Because now the antenna is operated from the 3.1 to 10.6 gigahertz. Constant polarization, impedance matching should be proper. Otherwise, the signal will not reach or it will not transmit. So efficiency are secondary. We deliberately try to radiate below noise level in UWB. So now these are the certain requirement for the UWB antenna design. So now here I have designed this hexagonal UWB microstrip antenna. This is the one of the basic antennas, hexagonal structure. So now here this hexagonal structure. So now this is a fabricated antenna. So now here this is a front side and this is a back side. This is partially ground because with the help of this partial ground, we design this UWB antenna. So now if we want to go in detail, then you people have to refer this paper. This paper is available online, right? So now just I am discussing here. So now this first initially we have simulated this antenna, then we have fabricated the antenna. So now here frequency domain characteristics. Now first we have to measure the return loss. So now here this S11 and now here this is below from 3.1 to 10.6 gigahertz. So now here the measured and simulated return loss of the antenna is shown here. So now they are perfectly fine. Then next is the measured group delay because now it should be satisfy the criteria. Otherwise, our receiving signal will not be improper. And then after that, I have to measure the E plane and H plane. So now here, this is the NQX chamber. In your college, you people can see. And now here, this is the NQX chamber. So now this is our hexagonal antenna. This is our my receiving antenna. So now this is the H plane. This is the E plane. So now I have to rotate this antenna, right? So now this will, one will give the H plane and one will give the E plane. So now the measurement setup of the radiation pattern in the NQX chamber. So now here the in frequency domain characteristics. Now just we compare the simulated and the measured. So now here earlier we have the simulated result. So now this simulated result will be compared with the measured result. So now for the different frequencies I have shown here. Now this is one is for the 4 gigahertz, then 7 gigahertz, then 7.4 gigahertz, and then 7.7 gigahertz, and then 7 gigahertz. So now here different simulated and measured E and H plane radiation patterns for the center is given from the 4 gigahertz to the 10 gigahertz. And then there is a comparison. So now here we can see the property, radiating property of the antenna. So now here we see now there is a low frequency to the high frequency, the antenna become a directional, right? And this is the time domain characteristics. So now here just I have measured this earlier is the frequency domain analysis. Now this is the time domain analysis. So most of the people are not familiar about the time domain analysis. In case of the time domain analysis, now just we have to transmit the pulse. So now here I have designed this UWB generated circuit. So now just I connected with the transmitting antenna. So now here the pulse is transmitted and now this pulse is received here. So when we receive the pulse and this pulse can be seen on the DSO. So now here this is a very high frequency oscilloscope, right? So now here this is the transmitter input. So here you see this is the rectangular waveform. So now 1010, this is a digital input is given, and correspondingly now there will be pulse will be transmitted with the help of the pulse generator. So now here at the receiving side we will receive the UWB pulse. So now this is the actual transmission. That's it. How the signal is transmitted actually, right? So now here this is whatever signal we give. So correspondingly now there will be pulse will be transmitted. So now this is a zoom view of the pulse, right? And then this the received output. So now just when we take the spectrum, so now here this is the spectrum. So now here this should be work from the 10.3.1 to 10.6 gigahertz. So now this is the received UWB pulse in their frequency spectrum is shown here. Another is the design of transmission line fed stepped match UWB antenna. So now here this is the front and back view of this antenna. This is another antenna. The antenna is designed on FR4 substrate with thickness of 0.8 mm and the electric constant is 4.4. Because now here thickness, now just you see 0.8 mm, very small in size, right? So now here, this is the design of transmission line fed step match antenna. So now here the parametric study of the ground length. So now just when we vary this ground length, the variation will be shown here. This is a parametric study by vary the patch length, and this is the patch width, then step length. So now when we vary the each very small, that is this is basically a procedure of optimization. So now when we vary it, then we can easily see the changes. And finally, the parametric study is completed. So now the return loss characteristics obtained after the patch and step parameters are optimized, right? Because optimize is required, because now just we have to find the exact. So now is not exactly follow the UWB range. So further optimization technique have to be adopted to get the impedance bandwidth exactly UWB from 3.1 to 10.6 gigahertz. That's why we require the optimization. So now here the various iterations the people will do, and finally they will reach to the goal, and then we say now that's our antenna is designed. So now this paper is also published. So now this you can refer this paper here. So now here another is the notch ground in transmission line fed step match UWB antenna. So now here there's a notch. Notch antenna means now here in case of the UWB antenna, now here we have a certain problems. So now that's why we require the notch antenna. So again there is a notch of a size 2.65 and 2.2 millimeter square have been introduced in the ground plane. So now here, this is the radiation patterns. So now at 4.5 gigahertz, the main lobe occurs with the magnitude of in H plane 4.5 gigahertz. The main lobe occurs in 180 direction with 2.8 dB magnitude. So now here, this is the far field gain pattern. So now here for the different frequencies. So now far field E plane, H plane radiation pattern of transmission line fed step match UWB antenna with notch ground at different frequencies 4.5 gigahertz, 6.5 and 10 gigahertz is shown here. So now the result of transmission line fed step match UWB antenna with notch ground. So now here this is the VSWR, sometime we measure. So now this is the graph of the efficiency. So now here this is radiating efficiency, and this red graph is shown the total efficiency. This is a graph between the gain. Gain is the important parameter. So now this is a gain versus frequency. So now here when our simulation satisfy our objective, then we have to go for fabrication. So now here this is the antenna is fabricated. So now here when we fabricate, and then finally we have to measure it. Earlier we have already discussed the measurement with the help of the vector network analyzer and all these. So now here this measured and simulated quantity is compared. So now it satisfied the criteria. So now here another design of CPW fed step match UWB antenna. Because now here coplanar waveguide antenna is very much needed for the biomedical application, because I have to design the antenna for biomedical application. So now in case of the biomedical, now suppose I have to put an antenna on the surface of the body, then the copper will should not touch to the body. That's why this is the one of the popular popular strip lines, that is the coplanar waveguide, planar transmission line, is used for design the antenna, because now here the ground planes and your conducting strip is on the same plane. So that's why this is the one of the most suitable for the antenna designing. So now here CPW fed step match UWB antenna was designed on the FR4 substrate. So now here this is again parametric study for the optimization purpose, and finally this is the gain versus frequency. So now radiation efficiency is 99.6%, total antenna efficiency is 97.4%, and gain is shown in this figure here. And then finally the radiation pattern is shown here. So now here the E plane and H plane radiation patterns are shown on different frequencies. So now here this is the comparison between the simulated and the measured result. So now here the for the low frequency and high frequency result are compared, and then later on now just we have to measure the again radiation pattern. So now this is the antenna under test, and now this is the horn antenna. So now just we measure the E plane H plane radiation patterns. So now here this antenna is working on UWB. Then performance analysis of a CPW fed step match UWB antenna in presence of human arm model. Because my objective is what? I have to design the variable antenna. Variable antenna means now this antenna will be put on the human body. So now here for this purpose, now we will use the human arm model, that is phantom. So now here there is a bond density, there is a relative permeability. These are the data is given here. So now here this is the antenna I have to put. So this is the brown shape. This is the shows the skin, then fat, then muscles, then bone. So now they have a different relative permittivity, conductivity, and thickness. So now with the help of this, now I have to develop the model. Then we have to simulate the thickness of the tissue has been chosen arbitrarily, but dimensions are within prescribed range. The antenna has been placed at a distance of 1 mm from human arm of size 64 into 52 mm square. So now here the performance analysis was conducted in presence of human. So now here these are the S11. Then radiation pattern with and without arm model. So now here there is a comparison is shown here. And then finally the design and development of flexible antenna. So now here these are the final dimensions is came out. So now here this is design on the RT Durite flexible substrate having a epsilon R 2.2, right? So now here these are the parametric variations, and this is the flexible UW antenna. That's the radiation patterns. Then again this is the gain and linear efficiency. So fabricated on RT Durite substrate, relative permittivity 2.2, and thickness of the material is only 0.127 mm. And then results have been measured in the Rosen-Schwarz 50 GHz VNA. So now here this is the actual fabricated antenna, and now this is the measurement. So now here this is the value of the S11 simulated and the measured. And now here now come to the testing of flexible UW antenna in proximity to the human body, because now here in simulation we have used the human arm model. So now here now you see now in this figure this antenna is placed on the body. So now here we have put on the arm, bicep, and thigh. So now here there is a low frequency cam. So this is 1.8, 2.4, 2.1. This is the upper frequency. So now here these are the results in presence of the human arm. So now this result is the in presence of human arm. This results in the proximity to bicep, and this is for the thigh. So now here we are seeing now these are the this antenna is suitable. So now here the maximum shift in the lower frequency is observed when flexible UWB antenna is placed near the human arm. Minimum shift in the lower frequency is observed near to the bicep. But in this condition, the impedance matching get deteriorated, especially in frequency around 2, 4.5 and 9 GHz. When flexible UWB antenna is tested near to thigh, the return losses are less than 10 dB for the complete UWB range. So now here the design and development of a conformal UWB variable antenna, because now earlier now antenna is cannot be bent. So now here we have to design a such antenna, so now we can easily wear it. So now RT Duroid, relative permittivity 2.2, and loss tangent, the thickness of material is this one. So now the structure of conformal UWB antenna for bending radius, because R is equal to 25 mm, RT is equal to 50 mm. So now this is for a 5-year old age children, and now this is for the young chap that is around 35 years of the age. So now their radius of the arm will be a 50, and now for this younger people now there will be 25. So now the some variation in impedance matching have been observed. If the antenna bending radius is less, so the parametric study of 25 bending radius has been considered. So again, there is a parametric analysis. So now just I will skip here parametric analysis, and finally now these are the results: efficiency versus frequency and gain versus frequency shown here, and these are the radiation pattern of this variable antenna. And now finally, now the my simulation is okay, then I have go for fabrication. So now here this is the measurement setup for conformal UW antenna bending radius of 50 and now here this is the 25. Now such this is a very small curvature, so 25, and these are the measured result is shown here. So now here they satisfy the our design. So now here the comparison of flexible UW antenna, planar and conformal antenna. So here there is a radiation efficiency, total antenna efficiency, gain, and all these are compared. And if you want to go in the detail, then you people have to refer this paper, and paper is available online. So now it's published in the World Academy of Science. So now just you download them and you read it. If you have any difficulty, then you can contact me, right? So now here these are the result of the flat antenna bending radius of 50, 25, and all these. Another is the experimental investigation of the breast phantom for tumor detection using ultra wideband MIMO antennas sensors. So now here we will use the breast phantom for cancer detection. So now here these are the phantoms. So normal phantom, single tuner, and all these. So now just we have designed this antenna, then we have tested, right? So now here this is the MIMO antenna sensor probe, and these are the results and their analysis. So now here this is the evaluation process of UMA sensor probe. So now here we have designed this antenna, and these are the results for the reflection coefficients and S parameters. And this about the detail of this paper is available. So now just you download this paper from the IEEE Sensor Journal. So now experimental investigation of a breast phantom of tumor detection using ultra wideband MIMO antenna sensors. So now here this is the radiation pattern, because this is for 3 gigahertz, this is for 10 gigahertz. So result of the radiation pattern with each element is analyzed. And this is the breast phantom modeling. So now just this is a procedure. So phantom are structured in 3D spherical shape and replica of actual breast. Their permittivity and conductivity of are mimicked, and based on the different layer of breast, skin, fat, glandular tissues, and tumors. So we develop 3 kinds of the phantom for experimental investigation. That is the normal phantom, homogeneous phantom, and with single tumor, heterogeneous phantom with multiple tumor. So now here these are the phantom involved: normal phantom, single tumor. So now here you can see this is single tumor, this is the multiple tumor. So now here the two tumor is shown here. So homogeneous phantom is developed using this distillized water, sodium chloride, polyethylene powder, agar powder, and propylene, xanthan gums, and formalin. So now these are the material used for the design this phantom. So in the process of phantom preparation, so this is the preparation method is shown here. So now here the cancer cells are mimicked by inserting glycerin ball inside the development breast model. So now finally this breast model is ready, and now this is used for the actual measurement purpose. So now here just we have put the one of the stand here. This is the phantom under the test, and above this now just we have put the antenna, and this antenna is connected to the VNA, and finally now the results is came. So now here this is the value for the S11, that's the normal phantom, single tuner, and multiple tumors, because we have designed the 3. So now here these are the results. So now here the variation of the measured isolation parameters of the UMA sensor probe with phantom. So now here this is S12, S13, and S14. So now with the normal phantom, single tumor, and multiple tumor. So now here finally that is a principal component analysis is done to detect this cancer. So now PCA results of the magnitude of the reflection parameter of the probe with the phantom. So now this is the first we have taken the with the help of the reflection to identify exact difference between normal and malignant phantom. PCA analysis carried out on the reflection parameter. The PCA is statistical unsupervised machine learning method in which complex dimensional data set is converted into 2 principal components. So now here this is the phase analysis of the probe with the phantom. So there is a one is related to the magnitude and one is related to the phase. So now here this is a phase analysis given. So now with the help of this, now the PC analysis of the phase angle of the reflection parameter. So now here for the normal phantom, so now here this is cam, and for single tumor, so now these results shows, and this is for the multiple tumor. Finally, the observation of data of the simulated maximum and average SAR, specific absorption rate. So now here at the frequency 3 gigahertz, so now these are the values for 10 gigahertz and 70 gigahertz. And finally, we have compared them for the multiple tumor, single tumor, and normal phantom. So now here this is the specific absorption rate analysis for the phantom. So now here summary in this work, the three phantom, normal, single tumor, multiple tumor were experimented using UMAS sensors. Sensing mechanism is simple with user comfort and data, and has wide range of characterization capability of the phantom based on several parameters evaluation. SAR analysis of the phantom using UMAS probe is well distinguished the normal and malignant phantom. This is the another non-invasive micro multi-element sensor for dielectric characterization for breast phantom tumor detection. So now here again we design a different antenna, that is MMSP sensor probe and evaluation. Again same procedure. So now here this is a phantom for measurement. So now here we design this antenna. This is a MIMO antenna. So now this prototype is developed. So now here these are the steps. So these are the reflection coefficient results, and these are the comparison of the simulated and the measured results. So the proposed micro multi-element sensor MMSC has a larger operating bandwidth, 2.4 to 30 gigahertz, and lower mutual coupling among the sensing element is attained with the average value of S21 is smaller or equal to minus 30 dB over the entire inserted band. So now here these are the simulated radiation pattern of the MMSC sensors. So now here these are the radiation patterns at the 2 gigahertz and 20 gigahertz. So development of the phantom model, again the same procedure that we have chosen the certain parameter we have taken for the skin, fat, and the tissues and tumors. And the hemispherical shaped breast phantom is mimicked using dispersive material which has similar properties of biological tissues. So the dimension, relative permittivity, and conductivity of developed models of the breast are collected in the given table. So now here this is the tumor. So now you can see here this is the fabricated phantom. Again we have put the antenna on this, and now PC analysis and results is shown in this figure. So now here this is the chemicals are used to design this phantom fabrication. So the phantom, then put the antenna here, then we do the PC analysis the same as earlier. So now here these are the reflection coefficients. So difference between the maximum value of reflection coefficients are shown here. So measured result with the mutual couplings. The principal component analysis of the results of the measured reflections coefficient is shown here. So the maximum SAR for tumor locations. So now here there is a SAR values is given for the different frequencies. So now here in the conclusion we can say in this work an efficient and low cost modality using MMSC is presented for tumor detection inside the dense breast. Conventional sensor probe can measure and analyze single parameter of the sample under test. Hence sensing probe is offered the wide range of measurement capability as compared to the conventional probe. Limitation of carried out work is exactly location of the tumor could not be identified by obtained result, or simply we detect only the tumor. So now this is the biomedical application of the antenna. So now we can design any kind of the antenna that can be suitable for the biomedical. So now here just I have discussed the actual fabricated antenna for the variable purpose, right? And similarly those who have interest, and they can easily design the antenna for the implantable also. So now this is a thanks, because now I think time is more than 1:15. So now thank you.
Thank you, sir. Thank you. Thank you for such informative session. We are very thankful that you spent your valuable time with us, sir. Thank you very much, sir.
I also thank you, sir. I'm coordinator for the program, and I really extend my thanks to you for accepting our invitation and giving such a informative session on antenna in biomedical application. And because time is short and lunch time is there, so I would not ask any queries. If any of the participants have any query, they can contact on email to sir.
Yes, yes.
Because
You.
one time I did not invite queries. Thank you very much, sir.
So now, thanks to all of you, Shyam Sundarji, Pankaj Sharmaji, and whatever seen on the screen, and your principal sir also, for organizing such nice ATAL FDP in your college. So
Thank
very
you,
good team of the your college. I appreciate this team. So thanks to all.
Thank you, sir,
For
and thank
inviting
you all
me.
the participants also. Thank you all the participants. Thank you, sir, again.